Okay, I think we'll get started. First of all, thank you for coming. Welcome to the 2017 iteration of the Joburg Spring School. So this morning there will be 3 sets of lectures. The first set of lectures will be by me. It's basically when you're approaching physical problems, oftentimes you sort of know what the answer is, but actually I can do a detailed calculation, and I'll try to explain some tools for guessing the answer. Then Jaco will tell us about giant magnons and magnon scattering, and finally in the morning, Yuki will tell us about integral spin chains. So the afternoon session will be 2 tutorials, one by me and one by Jaco on our respective topics. So my goal today is just to formalize ideas that are somewhat familiar to you already, namely units and dimensional analysis. There's a result from the early 20th century, around 1915, called the pi theorem. The pi theorem essentially enables us to write equations for physical laws in terms of dimensionless quantities. So the formula of the pi theorem will then enable us to guess the answers in many physical contexts, and I'll show some applications of the result. So on Wednesday, in the second lecture, I want to use these ideas, namely dimensional analysis, to motivate the renormalization group equation, which is one of the fundamental insights in modern physics. The renormalization group equation is a way to organize physics according to scale, and this relation essentially follows just by using dimensions of quantities in physics. So the tutorial will discuss applying these ideas to solve what are called Fermi problems. So famously, Fermi predicted the yield of the Trinity test just by dropping pieces of paper. So we'll try to reproduce that calculation and others in the same spirit this afternoon. So that's the plan. Please stop me if there are any questions as we go along. So we know that in physics, we essentially have dimensionful quantities. And dimensional quantities have units associated to them. So for example, velocity is a distance traveled per unit time. So there's a unit associated to velocity, say meters per second. So when we're learning introductory physics, we usually work in the so-called NKS system, meters, kilograms, seconds, or the CGS system, centimeters, grams, seconds. And all of our physical laws are formulated in terms of objects with the appropriate units. So we have fundamental units. So for things like mass, length, and time, and also things like current and temperature and whatnot. And we build other quantities based on these fundamental units. So we can think about these fundamental units as defining unit vectors in some vector space. So for example, for mass, you can assign vector as follows. And some derived unit, like force. Force is kilograms meters per second squared. So that's mass, length, time to the minus 2. We can assign this to be a vector in the space defined by these unit vectors. So force then is going to be the vector 1, 1, minus 2. So the other quantities that have units are also similarly defined. We figure out what the units of the thing are, and we assign a vector in the space with these unit vectors as the basis. So this is really nothing mysterious, as we've always been doing in physics. But it's interesting that there's a group structure that's built in here. So if you look at the structure of these units, we have something which is associative, commutative, and there's an integral multiplication operation with these things. We can multiply things, we can invert things in this zone. So this essentially defines a free abelian group. So the familiar units we have give us a free abelian group. The free abelian group is generated by these unit vectors and also by any dimensionless quantities that are in the game. So we can always construct dimensionless quantities. So for example, force inverse times mass length times the minus 2 is dimensionless. So given a dimension-full quantity, there's dimensionless quantities, and these dimensionless quantities, together with these unit vectors, form this free abelian group. So this is essentially how one formalizes the idea of dimensional analysis, and this was already done by Bertrand and Rayleigh in the late 19th century. So this is very old physics, very old intuition that goes into this. So the Buckingham pi theorem is a result that comes from 1915 or so. The reference is a paper in Nature called The Principle of Similitude, and the theorem goes as follows. So an equation involving n physical quantities, so n dimensional objects, constructed from k independent physical units so far k is 3, corresponding to mass, length, and time. So we have n physical quantities constructed from k independent physical units, may be expressed as a relation among pi 1 to pi p dimensional parameters. Where p is n minus k. So this result is just a simple consequence of the rank nullity theorem in linear algebra. So again, this is not a very deep result, but it's a result that enables us to write equations, say, of the form phi 1 to pi p is 0, and all physical laws can be expressed as the equation of this type in terms of these dimensionless quantities. So the goal here in the remainder of the lecture is to just look at various applications of this, this very simple result. Okay. Any questions so far? Okay, so the thing with dimensional analysis is we get the answer right up to a number. We can't get factors of 2 or pi or things like that by analyzing equations in this way. We can just sort of get the right behavior for the various quantities that appear to describe some physical phenomenon. So you're going to be correct up to various numbers. Usually these numbers are order 1 or order a few. So just by following your nose, you're not too far off. Okay, so it's useful to do a very trivial example in order to illustrate this structure. So let's just start with some example from classical mechanics. So for example, take the pendulum. We know how the pendulum oscillates at small angles. We know that the pendulum is acted upon by the force of gravity. The acceleration due to gravity has units of length time to the minus 2. And we also know that there's a mass in the game, and there's a length in the game, and there's a period for the pendulum. Okay? So we expect some equation that involves g, that involves the mass, that involves the length, and that involves the period t. And this equation is something equals 0. That's straightforward just by the setup of the problem. So we want to reduce this equation to something of the form. So we know that m, l, and t define our basis. So there are 4 physical quantities that appear in this equation. There are 3 basis elements. So we expect the equation of the form f of pi equals 0 for the appropriate pi. Now we know what pi is just by inspection here, but let's try to derive this in a formalistic sort of way, just so that we know what we're doing. We can apply this formalistic setup in more complicated environments where we can't just look at the problem and determine what the form of pi is. So we write a matrix. Matrix A is going to be given to us by the form of these various quantities that appear. So there's 0 mass to the 0 here, length to the 1, time to the minus 2. So the first column corresponds to g is 0, 1, minus 2. Next column is m, that's 1, 0, 0, l, 0, 1, 0, time 0, 0, 1. So we have a matrix which isn't square. The number of columns in the matrix correspond to the number of variables, and the number of rows correspond to the number of basis elements that define the various vectors that appear in our notation. Okay? So this matrix has a null space, and the null space is just the set of vectors such that A acting on a vector is 0. So the generic element of the null space, x, is going to be some number, lambda, times 1, 0, minus 1, 2. So you can act this matrix on this vector, and you'll get 0. Okay? So this essentially tells us that the dimensionless quantity we should consider, pi, is going to be mass to the first, length to, it's going to be, the first variable here is g, m, l, t. So it's g, first power, no powers of mass, length to the minus 1 power, time squared. This is just, canceling out the units in g. So it's obvious this has to be the correct answer. We found this by solving for the null space, the kernel of the map given by this matrix. Okay? So what this tells us then is that we solve this equation for t. This is just some number, it's dimensionless, and t will scale like square root L over g. So the constant in front is 2 pi. That's not something determined by dimensional analysis. We get the form of the period just by looking at these parameters. And we notice the period is independent of the mass of the object, which is exactly what you expect for a pendulum. So the simplest example is one that illustrates the physics that we understand very, very well. We want to examine physics in settings that are somewhat more complicated than the very simplest example that we can consider. Everyone happy with the example?
Would you have added, let's say, air drag into this thing, or the size of the ball, of the mass thing?
Sure,
like
but this is simple.
Okay.
Yes, you can. And those are all dimensional quantities as well that enter into this, but it'd just be more complicated. So our second example is is also rather familiar, and essentially determines the way we think of physical theories. So we can think about Galilean mechanics. And we can think about taking Galilean mechanics as our starting point. We think about tweaking Galilean mechanics in a number of ways. So one way of tweaking Galilean mechanics is to add gravity. We add gravity, we turn on G Newton, and we get Newtonian gravity. We can ignore gravity and turn on another parameter, h bar say, and we get quantum mechanics. So this direction is G Newton, this direction is h bar. We can also turn on a finite speed of light, so 1 over c is finite, and we get special relativity. We can do these things in various combinations. If we turn on both special relativity, we turn on both the speed of light and h bar, we'll get quantum field theory. If we turn on both Newtonian gravity and 1 over c, we'll get general relativity. If we turn on h bar and G Newton, we'll get some Newtonian quantum gravity. It's a strange sort of theory, but it exists. If we turn everything on, we'll get some quantum theory of gravity, which we don't fully understand. So we organize theories by looking at turning on these various deformation parameters, G Newton, 1 over c, and h bar. So the idea that you organize the kind of theories we have in this way was realized by a fellow named Mandelstam, and if you organize these things properly, it's called Bronstein's cube. So we have these various parameters that we turn on, and these quantities, h bar, G Newton, and 1 over c, are dimension-full quantities. So you can work out very easily if units of h bar are mass, length squared, time inverse. These are the units of the action. The units of G Newton are mass inverse, length cubed, time to the minus 2. And the units of C are length per time. So we can formulate a matrix similar to the matrices that we saw previously. This matrix will have rows, will have columns corresponding to these physical quantities. So 1, 2, minus 1 for h bar, minus 1, 3, minus 2 for G Newton, 0, 1, minus 1 for C, and we're working at a basis defined by our basis vectors, which are mass, length, and time. So this system has 6 parameters that are dimension-full, and their basis again has 3 parameters. So rank nullity theorem tells us we can construct 3 dimensionless invariants out of this, and they're given to us by the null space of A. Kernel of A is the span of a bunch of vectors, and these vectors are minus 1, 1, minus 1, 2, 0, 0, minus 1, minus 1, 3, 0, 2, 0, and minus 1, minus 1, 5, 0, 0, 2. Now, this is just a basis for the null space. You can rotate these vectors among each other, take linear combinations of these vectors, in other words, and get another perfectly good basis. So the basis is not unique, so the variables that appear in the pi theorem aren't unique either. Remember, these things form a free abelian group, So you can compose them in various ways and get another perfectly good basis. But this basis that I've chosen is a very convenient basis because it makes certain quantities manifest. So these equations tell us that pi 1 is h bar inverse g Newton c inverse m squared. Pi 2 is h bar inverse g Newton inverse c cubed l squared. And pi 3 is h bar inverse g Newton inverse c to the 5th t squared. Just from reading off these the elements of the null space. So we recognize that based on these quantities, since the left-hand sides are dimensionless, we can construct a mass. This mass is the square root of h bar c times g Newton. We start the length. This length is square root h bar g Newton over c cubed, and a time, which is square root h bar g Newton over c to the 5th. These are respectively the Planck mass, the Planck length, and the Planck time. So the standard way of computing these things is to take powers of h bar, g Newton, and c, and organize these powers such that you get things which have units of mass, length, and time. We've circumvented this by solving for the kernel of this matrix. Okay. So again, we see a result which should be familiar. This lets us organize these physical quantities, and we can determine that there are these natural powers of mass, length, and time. And if we're considering a theory with h bar, c, and g Newton all turned on, theory of quantum gravity in other words, the natural scale, the natural energy scale associated to quantum gravity would be m Planck c squared. So typically, we work in units where h bar equals c equals 1. We can do some calculation wherein we don't need to worry about powers of h bar and c, so that we're working in units where mass equals length inverse equals time inverse. But at the end of the day, if you're comparing to experiment, you need to restore these h bars and c's and compare it to the outcome of the observation and match the theory to the experiment. So if you're doing experiments that involve all of these parameters, the natural scale to look at is obtained from looking at these combinations, and this is around 10 to the 19 GeV, which is some 16 orders of magnitude beyond what our accelerator experiments can probe. Everyone happy with this? So I want to do two more examples that focus on these basic ideas, and I want to thereby explore some nice physics that dimensional analysis can start teaching us about. So the first thing I want to think about is Hawking radiation from a black hole. So, roughly speaking, the idea is that there are certain solutions to general relativity such that the speed of light being finite means that certain things are forced to happen. So, if we look at the Einstein equations in general relativity, the Einstein equations tell us the tensor, which you can formulate using geometric quantities, and this tensor is equal to another tensor that corresponds to the presence of matter and the behavior of matter in space-time. So this equation is basically telling us about space-time's response to the presence of matter and energy, and conversely, the motion of matter and energy in a curved space-time. So the theory of general relativity was proposed by Einstein in 1915, and when Einstein proposed this theory, he had one rather trivial solution. The solution was flat space, basically. This is a second-order nonlinear differential equation. The standard technique for solving second-order nonlinear differential equations is to guess the answer and check that it works. So the only solution which Einstein had was flat space and slight deformations of flat space. So in the following year, 1916, Karl Schwarzschild looked at the most symmetric solution you can imagine for the Einstein equation. He made the ansatz, the solution was spherical. And he made the ansatz further that there's no right-hand side to the equation. So T mu equals 0. So given these assumptions, there's a solution. The solution is the Schwarzschild solution. And this is a metric for a black hole in general relativity. So the solution is such that there's an object, a surface, called the event horizon. And classically, the event horizon you can think of as there's an escape velocity associated with objects with mass, and the escape velocity beyond this surface exceeds the speed of light. So classically, when something falls in, it can't escape. Because in order to escape, the attractive pull of gravity is moving faster than light, which is forbidden by the laws of physics. So this event horizon is a feature of this Schwarzschild solution. Deep in the interior of the black hole is a singularity. At the singularity, curvatures blow up. And one of the assumptions that went into Einstein's theory, that space-time is smooth, breaks down. So at the singularity, we don't really know what happens in the framework of a classical theory. The hope is that some quantum theory of gravity will start resolving these singularities that we encounter in space-time physics. We don't have a good resolution for the singularity problem, even in a theory like string theory, for example. So it's an open question as to how to do this. There's some ideas, some more convincing than others. So, so we essentially have this picture for a classical black hole. I keep saying the word classical because I want to emphasize that things that are behavior that's somewhat unexpected happens in a quantum mechanical theory. So one of the upshots of quantum field theory is the vacuum is dynamical. So we can analyze the black hole in a semi-classical context. So semi-classical physics of black holes. And I'll just draw the cartoon picture. One can make these things rather precise. So for the purposes here, the cartoon suffices. So the cartoon is that we have the uncertainty principle. Delta E, delta T goes like h bar. So the uncertainty principle involving energy and time is rather different than the uncertainty principle involving momentum and position. And the reason is because time isn't really an operator in quantum mechanics. Time is a parameter in the Schrödinger equation, whereas x and p are bona fide operators in quantum mechanics. So Aharonov and Bohm pointed out that this uncertainty principle is somewhat more subtle than the uncertainty principle associated to position and momentum. But nevertheless, let's accept this behavior. So in small times delta t, we have large energy fluctuations, delta E, in the vacuum. So these large energy fluctuations can create, for example, an electron-positron pair. This is a chargeless object, so charge conservation is respected. You can imagine this happening in the vicinity of the black hole horizon. Momentum conservation says that if one of the particles is moving this way, the other particle is moving the other way. So an observer at infinity will see a black hole emitting these Hawking particles. This emission of Hawking radiation is isotropic and follows a black body distribution. So these particles that come out of a black hole follow a perfect black body. Okay, so it looks like the black hole is shedding mass. And eventually, as the black hole keeps shedding mass, particle, the observer at infinity, picks up this bath of thermal Hawking radiation, and the black hole gets smaller and smaller. As the black hole gets smaller and smaller, it heats up, so it starts emitting faster and faster and faster. And eventually the black hole evaporates, and the end point of this evaporation is one of the central mysteries of modern physics. It goes under the name of the information paradox. What happened to the information that formed the black hole, about the state which formed the black hole in the first place? How do you recover that? By looking at this bath of Hawking radiation. When quantum mechanics is a unitary theory, so that information should be recoverable, that this Hawking radiation seems to be a property of physics near the horizon, and there's a theorem in classical black hole physics called the O'Hare theorem that says the metric for the black hole is determined in 4 dimensions by the mass, the charge, the angular momentum. So we don't have really access to the fine details of what formed the black hole in the first place just by looking at the black hole metric. So it's an enduring question to understand how to recover this information in a quantum theory of gravity from the particles that you see at infinity. So that's the setup we have. I want to characterize certain aspects of this setup using the technology that we've developed. And again, just being very, very naive, we were able to get rather far in describing physics. So, because black hole radiation is thermal, we introduce one new parameter to the game. The new parameter we introduce is the Boltzmann constant. So the units of the Boltzmann constant are energy per temperature. So the units here are mass, length squared, times the -2 per Kelvin. So again, we want to set up a matrix, and to determine, suppose we want to find a temperature of the black hole as a function of the mass. So I claimed earlier that as the black hole is evaporating, as it's getting smaller and smaller and smaller, its mass is decreasing because mass conservation includes these Hawking particles at infinity. So the mass of the black hole is decreasing as this evaporation proceeds. I claim the black hole is getting hotter. So let's see how that dependence works out. So again, we construct some matrix, A, and I want to solve for the temperature. So the rows of the matrix correspond to mass, length, time, and temperature now. And we want to consider a temperature as a function of the mass. And in our game, we have the usual parameters, h bar, g Newton, c, and now we have k Boltzmann, 1, 2, -2, -1. So there are 6 parameters in the game, and there are 4 constants of nature, h bar, g Newton, c, and k Boltzmann. So again, we solve for the null space of this matrix. So the null space, kernel of A, is a span of -1, -1, 1, -1, 3, -1, and 0, -2, 1, -1, 1, 0. So you solve for the kernel by essentially doing Gaussian elimination on this matrix A. So there's a formal procedure in linear algebra you follow, where you just type it in Mathematica and it spits out the answer, which is what I did. The second expression, the second element of this, the second basis element for the kernel basically recovers for us the Planck mass. So it's not anything that we haven't seen previously. The first element, however, tells us that there's an invariant we can form, pi 1, which is 1 over the temperature, h bar c cubed over g Newton k Boltzmann times the mass. So that's just by reading off what this vector means. So this tells us then the temperature scales like h bar c cubed and g Newton k Boltzmann. So indeed, as mass is decreasing, the temperature is increasing. And this answer is perfectly right up to a factor of 8 pi in the denominator. So we can get interestingly complicated physics just by looking at units of things. So we also know that because black holes have temperature, they're thermodynamic objects. We noticed, for example, we claimed, for example, the Hawking radiation is a black body. So we also know that consistent with things like the energy conditions in relativity, the area of the horizon as a function of time in a physical process increases. So these motivate for us laws of black hole mechanics, which are analogous to the laws of thermodynamics. So in particular, because the area of the black hole is increasing, it's non-decreasing anyway, as a function of time, it means in physical processes that are interesting, there's an entropy you associate to the area. So again, this is something one can easily motivate using dimensional analysis. So we know the physics associated with Hawking radiation happens near the horizon. The horizon size is characterized by an area. So the matrix you want to consider is something where the first column of interest has to do with area. So it scales like squared. And again, the physics here is related to h bar g Newton c. So we have 1, 2, minus 1, minus 1, 3, minus 2, and 0, 1, minus 1, corresponding to physical parameters. And the null space here consists of a single basis vector. So the null space is lambda x, or lambda real, and we have 1, minus 1, minus 1, 3. So this tells us that the invariant is area times c cubed over h bar g Newton. So you want to form something with units of entropy. It's going to be kb times this invariant. So the fact that the entropy of a black hole, that corresponds to Hawking entropy, scales like the area is just a consequence of dimensional analysis. Okay.
Sorry.
Yeah.
Why didn't you introduce the Boltzmann constant in that matrix?
Because I knew the answer. In principle, you can. This invariant you would have arrived at even if you introduced the Boltzmann constant.
Yes, because I think we have Boltzmann constant appear in the end when we introduce the entropy. So if we put it in the matrix, it will appear from the beginning, right?
Yeah. Yes.
For the temperature, the black hole, previous example. So is there somehow implicit there that the observer is at this infinite proper distance from from the black hole, because one could possibly ask what will happen if you go very near the black hole with that length, proper length of the observer effect is analysis, because the temperature would then be different.
Right, I'm working with the asymptotic observer here, and the asymptotic observer is sensitive to certain parameters. So these are physical constants of nature. The mass is an ADM quantity the observer at infinity measures. So these are the things that are accessible to the observer at infinity.
So one could not possibly hope to get the answer for an observer near using the.
Well, it's be redshifted somewhat. It'd be dimensionally the same.
No, in the sense that like, it should also tell you that when you get too close, it just shoots up, the temperature just increases and stuff. So it should also have that dependence. I mean,
That's detailed dependence, which you don't get from dimensional analysis. Though. That's a prefactor. Okay, so the next example I'm going to look at is also something which one encounters in quantum field theory. It's called the Casa Aircraft. And we'll see in the problems this afternoon that the Casimir effect leads to something very curious about the speed of light. It turns out that the speed of light can be exceeded by the speed of light. And this is something which is a physical effect which is basically not measurable. But we'll explore that in the exercises. So consider two parallel infinite conducting plates. So there's a separation between these plates, which is d. So you bring these infinite plates very close to each other. And classical electrodynamics tells us that if these plates are uncharged, there's no field in the game. And because there's no field in the game, plates just sit where they are. Nothing happens. However, we know the vacuum in a quantum theory is dynamical. So because the vacuum is dynamical, for example, the vacuum is pair-producing electrons and positrons. So the virtual photons interact with these electrons and positrons in between these plates. These virtual photons that are present give us an electric field, or a magnetic field. So quantum electrodynamics, these virtual photons produce a field, and as a result, these plates are no longer static. It turns out these plates are attracted to each other because of these virtual photons. And that's called the Casa effect. The force is going to be a function of the separation of these plates, and it's also going to be a function of h bar and c, since these are quantum mechanical and special relativistic parameters. This is a non-gravitational setting, so the force is electromagnetic in nature, not gravitational, so there's no G. Let's compute the force per unit area. So the force per unit area is a pressure, and this has units of mass, length to the -1, t to the -2. So again, we set up a matrix, A. This matrix has 1, -1, -2 as its first column, and then it's a function of the distance between these plates, so that's a length, 0, 1, 0. And then we have h bar and c, which are 1, 2, -1, and 0, 1, -1. So again, we solve for the kernel. And the kernel is given by a basis, vector x, which is -1, -4, 1, 1. So So we form an invariant, pi, which is 1 over pressure times distance to the fourth with h bar c in the numerator. So the force per unit area goes like h bar c over distance to the fourth. If you do a careful calculation, you work out the prefactor. The prefactor turns out to be minus pi squared over 240. The minus sign tells us the plates are moving towards each other. This is Casa Aircraft. So again, just dimensional analysis tells us the basic answer. The curious thing is that if you consider the speed of light between these plates, the speed of light between these plates is slightly faster than the speed of light in ordinary vacuum. That's called the Schoenhorst effect. So light can travel faster than light. What this means is that there's a difference in principle between the speed of gravity and the speed of light. So in principle, there's an experiment you can do that measures this Schoenhorst effect. The thing is that the effect is so small that in practice you're not going to measure this. Okay, so I want to conclude by making a few remarks on what are called Fermi problems. So you're probably familiar with things like, say, the Drake equation. The Drake equation purports to measure the number of civilizations in the galaxy. And it does this by looking at things like the rate of star formation, the probability of finding planets around a star, which these days with exoplanets looks to be 1. The probability of finding a planet in a zone supports life, probability of intelligent life evolving and deciding to communicate, and us being able to detect these signals. And this lets us measure the probability of listening and finding some other galactic civilization. So these types of problems are solved essentially by dimensional analysis and by assigning reasonable numerical values to parameters that appear in the story that are dimensionless. So looking at these Fermi problems is a way to use dimensional analysis to guess the answer for things. So the canonical Fermi problem is how many piano tuners are there in the city of Chicago? This was an exam question that Fermi gave when he was on faculty at Chicago. I don't know what class it is, but it's relevant for any class, so probably is one of these problems that one solves by estimation. And you can look up the answer in the phone book and figure out how many piano tuners there are in Chicago, but the estimate is pretty damn close. The other canonical Fermi problem is one we'll work out in the tutorial. During the test for the first atomic bomb at Trinity, as the explosion was happening, Fermi dropped some pieces of paper. And the pieces of paper traveled 2.5 meters. So from that 2.5 meter traversal of these sheets of paper that Fermi dropped, he was able to estimate the strength of the atomic bomb. Again, using dimensional analysis. So we'll explore some of these problems in the tutorial. In the second lecture on Wednesday, I want to illustrate the failure of dimensional analysis, and I'll come up with some example that makes it clear that dimensional analysis, while getting the units right, can also be colossally wrong in describing the physics. And then I'll use dimensional analysis to motivate the normalization group. Okay. So thank you. We'll take a break before the next lecture.